let's look at all different types of system piping that you would find on steam heating systems. And we'll start out with the most basic one, and that's called a one-pipe parallel flow with a wet return. Now, by wet return, I want you to notice this dotted line here, because that's the center of the gauge glass, and everything below that dotted line is underwater. It's always underwater. So we call it a wet return. There's the Hartford loop, and this is one-pipe steam. You can see the vents on the radiators, graphically anyway, and a main vent near the end of the main. Now, the pitch has to be 1 inch and 20 feet in the direction of flow, which isn't much, but when we have parallel flow, meaning the steam and the condensate are both going the same way, the pipe has to be at least 1 inch and 20 feet. What I want you to watch out for is the loss of that pipe, and that often happens over time, you know, when hangers settle, or if they've had asbestos removed and the abatement people came in and removed the hangers and didn't properly support the pipe again, or if people hung things on pipe. You know, I often see people do this, and even at homes. I remember looking once at a guy's house where he bought a heavy bag, like a boxing bag, because he wanted to get in shape, and he hung the heavy bag, which was filled with a lot of sand, on a steam pipe, and it caused the pipe to sag. And oh yeah, he's down there banging away on the heavy bag, and the pipes are loaded with asbestos too. So he's getting healthy. Every time he hits the bag, he's sucking a lungful of asbestos. Nice. But it caused the pipe to sag, and his complaint was he suddenly had this wicked water hammer that he never had before. And I asked him when it happens, and he says whenever the system first starts up. Well, if you can imagine, you know, you hang a heavy bag like right here, and it's hanging down. It's got a couple hundred pounds of cement, or not cement. That would be bad for your fist. Sand inside of it, and the pipe takes this sag. So on startup, the water is stuck in the sag because it can't drain. Because you know, water won't drain downhill if there's no downhill. So the next time the system starts up, you get water hammer on startup. So that's why I'll always ask when it comes to water hammer, when do you hear it? And if you're hearing it on startup, the first thing I look for is the pitch of the pipes. Did we lose it? Whether or not they took off insulation and didn't replace it, because every steam pipe ever made is supposed to be insulated. And if you remove the insulation, you're going to get a lot of startup condensate when those pipes are going from ambient temperature to 215 degrees. And often that excessive amount of condensate in the pipe that was not designed to handle it, because the pipe is supposed to be insulated, will create water hammer. Too much water, too much steam in a pipe, you're going to get banging. So I'll always ask, when they tell me to have hammering, not just what does it sound like, but where is it, when does it happen, and where is it coming from? Where is another thing, because if the system is running for a while and then you start to get hammering, and it's happening down here at the end of the main, look at this thing called the A dimension, which I'll explain in more fully in a second. But the A dimension is the distance between the bottom of the lowest horizontal steam carrying pipe and the boiler water line. And that is designed to put the water back in the boiler. Depending on the weight of the water in this pipe, combining with whatever steam pressure is in this line, to put the water back in the boiler. That's why we call it gravity return. If the pipe gets clogged here, the wet return, and it will, because this is an open to the atmosphere system, so at some point this is going to fill up with mud. When it fills up with mud, the water is not going to be able to shove its way through that mud, so the returning condensate will just creep up here and peek its little face over the end of this line, and when Mr. Condensate meets Mr. Steam coming down at that line, Mr. Steam wins. And you start to get this banging, smashing water hammer, and it's always going to happen near the middle of the cycle. So that's how you know what's causing it. That's when you begin to suspect that these pipes are suffering from the steam version of arteriosclerosis. So about that A dimension, as I said, it's got to be 28 inches from the boiler water line to the bottom of the lowest steam carrying pipe, wherever that is in the building. And here's why. When we're operating, let's say that there's 2 pounds of steam pressure inside the boiler. Now, when the steam leaves the boiler, it loses energy due to friction and by condensing. So by the time we get out to the end of the main, we're not going to have 2 pounds of steam pressure left. That's impossible. This is not like you're dealing with compressed air. This is steam. It's going to change state. So by the time it gets out to the end, even in a big building, we may have 1.5 pounds of steam pressure. Now here's the problem. Think of this as a scale. You got 2 pounds of pressure on this side of the scale and only 1.5 pounds of pressure on this side of the scale. So the tendency is for the water to push out of the boiler and go up this line. So let's accommodate it. This is where the A dimension comes in. We're going to give it a vertical distance that's equal to 28 inches. Now a column of water 28 inches high happens to exert 1 pound of pressure at its base. So if I've got 1 pound of static water weight and 1.5 pounds of leftover steam pressure. That gives me 2.5 pounds on the return. There's only 2 pounds of pressure in the boiler, and that's how the water is going to flow by gravity from the high pressure into the low pressure, relatively speaking, of the boiler, and that's how we get the rabbit out of the hat. So that's what the A dimension is about. You need to measure this. If you're moving a boiler and you see that the boiler's in a pit, that's probably why the boiler's in a pit, so they can get it low enough to provide the A dimension. If you decide to put the boiler out of the pit, you might have water hammer after you're done working, like they never had before, like you won't believe. Now, since return lines do clog up because systems do corrode, many of the old-timers use parallel flow with a dry return, meaning that instead of dropping directly into the wet return and coming back this great distance underwater, we're going to come back above the water line and pitch 1 inch and 20 feet both ways. But notice now how your A dimension is no longer out here at the end of the main. It's now shifted over here back in the boiler room. And once again, this may be the reason why the boiler is down in the pit. So when you're changing a boiler, you have to wander out in the building and find that lowest horizontal steam carrying pipe and measure from there down to where your new water line is going to be. And here too, you see this loop where we drop down to go into the Hartford loop? The reason why we drop down like that and form a P-trap is if we just came directly back into here, the steam in this line, as the boiler steamed down, could have access to the return, meaning the condensate coming back, and that would give you water hammer here during the near the end of the cycle. So we always drop down to the bottom and come up into the Hartford loop. And please provide some valves here, because I guarantee you that all the schmutz in the world is going to wind up in that U-tube right there. And when that happens, you're going to get water hammer here. So much of this is common sense. It's just think like steam, think like water. What would you do? That's what I'd do. One pipe counterflow is a very unusual system that's found in buildings, smaller buildings. This line that runs out that carries the steam and the condensate in the same direction is usually never more than 100 feet long. So we're feeding one pipe steam radiators, and the pitch now has to be double. With the other systems, we needed 1 inch and 20 feet. Here we need a minimum of 1 inch every 10 feet. And the pipe has to be bigger in size too. So if you're not sure what size pipes you need, get a copy of my book, The Lost Art of Steam Heating, or get a copy of my book, The Golden Rules of Hydronic Heating, because in that book I show every pipe size in every steam system and the maximum load that could be on that. So if you're having a problem with water hammer on a job like this that's one pipe counterflow, you would go out and you'd measure the radiators for their total EDR load, and then you would look at the size of the pipe to see whether the size of that pipe in this system could handle that radiation load, because it might be that somebody added radiators to the line over the years, and that's why it's having a problem. That's why you can't get heat, or that's why there's water hammer. And here again, notice how the A dimension is back here in the boiler room. So feeding steam, doing the near boiler piping for what the boiler needs according to the manufacturer's specification. We're feeding into the top of this main and dragging the condensate down the bottom of the main, so counterflow. The Mills system, Mr. John Mills, that genius who worked for the H.B. Smith Company. This is what he did with this job where you got one pipe steam in a big tall building. Say it's a 10-story building. You come out of here with what might be a 12-inch screwed pipe. You go all the way up to the top. You put a big air vent up there because you want to vent all the air out of that big 12-inch pipe. Imagine a 10-story building with a 12-inch pipe inside of it. That's a lot of air. So vent the air very quickly out of there. The steam's going to get up here real fast. Vent the air out of here at the end of the main that goes around the perimeter of the upstairs, and you're going to get rid of the air out of that, and then you down feed, because steam doesn't know up from down. It's just looking for an air vent, and it finds them on the radiators, and it finds the air vents at the base of the risers. So the steam's going to go chasing toward the air vents. Your A dimension is now the distance between the boiler water line and the bottom of your lowest main vent. So the Mills system, it was a beautiful way of heating tall buildings with one pipe steam by getting everything up to the top and then down feeding to the radiators. Steam does not know up from down, it just knows out. It's looking for high pressure, going to low pressure. Now in some of the bigger buildings, they wanted to use two-pipe steam. I gave you some examples earlier about the advantages of a two-pipe radiator. It just feels better. Plus you're able now to throttle the inlet valves, so if you want the radiator to heat partway, you can shut down a little bit of the steam. If you want it all the way, you open the valve. One pipe steam was open or closed on the valve. You can't control that, but here you can. So in many buildings, they gave us this option, and they would now have thermostatic traps on the radiators, like that one I showed you in the New York Public Library that had the pneumatic system in it. And at the end of the main, we have float and thermostatic traps. which will stop the steam from moving through the end of the main into the dry return, because if it wasn't there, steam would go down the end of the main and right into the dry return, meaning the condensate coming out. You destroy the trap and you'd have water hammer. So F&T traps stop the steam here. Thermostatic traps stop the steam there. We have a main vent at the end of the main. Steam pushes the air through the traps. Before it can trap steam, it must vent air. It vents air into the return line and out of the main vent. Now over here, I'm showing you, instead of an A dimension, what I call a B dimension, which is the distance between the end of this main and the boiler water line. Since there's no steam pressure in this return line, because of the F&T trap, the only thing I have going for me to get back in the boiler is the weight of the water. And if there's 2 pounds of pressure in the boiler, I have to have at least 30 inches of static weight here per pound. So a little bit more than 28 inches. So I would have to have, say, 60 inches of height here of water to build up in order to push through a boiler that's operating at say, 2 psi. If I didn't have that, the water is going to back up into the main. That's 5 feet, right? The water is going to back up into this return main and close the air vent. It won't hammer because there's no steam in this line. But if somebody came along, the superintendent, and cranked the pressure control up, the water is going to back up here and flood the air vent. So now the whole building goes cold. So when I was younger and I was doing a lot of consulting, I would go out and I had this special screwdriver. I was one of the few people in New York who had this. It was a counterclockwise screwdriver. I was able to go up to a pressure control and turn it counterclockwise to lower the pressure. Most everybody had clockwise screwdrivers. All they knew to do was to raise the pressure. And in raising the pressure, they flooded the main vents. So I would go in, I'm this consultant, right? They're paying me a lot of money. I'd go in, I'd see the traps on the radiators, I'd see the traps at the ends of the main. I would see no condensate or boiler feed pump. I would recognize it as a 2-pipe gravity return system, and I would take my counterclockwise screwdriver and screw the pressure control down. That would cause the water to recede. The water would go back in the boiler because the pressure is now low. The main vent would stop being flooded, and the whole building would heat. And they would say, all you did was screw the pressure control and suddenly everything's working. I said, that's right. They said, well, why should we have to pay you for that? I said, because I knew that it needed to be screwed down. That's why you have to pay me for that. And your guy didn't know. So keep that in mind, right? Now here's a 1-pipe pumped return system. Let's say we don't have that static weight. We don't have enough weight, 30 inches per pound. So it's a 1-pipe system, and we've got a condensate, a floating thermostatic trap at the end of the main here, and another one over here. And here we got a condensate pump. So condensate pump is kind of a rude machine in that it doesn't care whether the boiler needs water or not. It has a float inside of itself, and the float is connected to this pump, and there's a vent on it. So this is just this big receiver, and there's a float inside. The float goes up, it turns on the pump. There's a check valve here, it pumps the water through the check valve. We don't need a Hartford loop here because there's a condensate pump. When you got condensate pumps, you don't need Hartford loops. We do need the equalizer because that's picking up the carryover water that you showed in that glass pipe boiler, or you saw in that glass pipe boiler before. So we're going to pump into the bottom of this, and that's fine if the boiler can accept that water as it comes back, because this condensate pump is not asking this boiler whether it needs it or not. But the challenge comes about when you put in a modern boiler, which is much smaller than the boiler you're replacing. So it's smaller and it has a lot less water in it. And the question then becomes, will the condensate pump, acting as it does, by not asking the boiler whether it needs it, will that be able to flood that new boiler? And if you suspect that it might, what I suggest you do is don't use a condensate pump here, but switch over at that point to a boiler feed pump. Now, a boiler feed pump has a larger receiver, as you see here, and it also has a pump controller, as you see here. So now what's controlling this pump over here is the pump controller, which senses the boiler water level, not the water level inside the boiler feed pump. So it's got an oversized receiver that can collect and store any water until the next cycle when it's needed. And the only way water can come into this boiler is if the boiler actually calls for it through its pump controller. So this is a good way to prevent that flooding problem, or solving the flooding problem if you have it. Replace the condensate pump with a boiler feed pump. A 2-pipe vacuum system now. Let me just back up a minute and explain something about vacuum system, because earlier I told you about Andrew Pohl and that system that he invented that was at the Dakota apartment house and the old post office in New York, which is now Donald Trump's big hotel. But the naturally induced vacuum system would happen with ejectors where they would suck the air out of the system. That was the Pole system. And as time went by, they invented these types of air vents that would go on radiators. And the air vent would have a little check valve in its outlet. And the main vents that went at the ends of the mains or near the ends of the mains had little check valves at the outlet. So the steam would come on, and it's a coal-fired system, and it would slowly nudge the air out of the system, and it would push out through these check valves on the air vents, and then when the steam condensed, the check valves would seat and not allow the air back in. So the entire system would go into a vacuum because the air couldn't get back in. Now, in the days of firing coal, that was very desirable because the coal fire was not steady. You know, it burned down during the day as the coal went down. So imagine back, you know, before we had gas barbecues and you were doing everything with charcoal briquettes. You make a fire, you cook your burgers and your hot dogs, and comes a point, you know, somebody shows up late for the party and you're out there trying to make one more hot dog, and you're standing there waving a newspaper trying to get those last coals hot to give you enough heat. Well, that was the challenge they faced in the coal-fired days, because as the fire burned down, there was less and less energy going into the water to make steam. But if they could use these naturally induced vacuum systems that would send the air through the check valves and not allow back into the air vents because of the check valve seating, they would be able to boil water at temperatures that got lower and lower as the vacuum formed. So later in the day, you might have steam leaving that boiler at temperatures like 150, 160 degrees going up to the radiators because the system would be in a tight vacuum. That got abandoned when we moved from coal to oil and gas, because now that you've got an automatic burner, when the thermostat shuts off the burner, the vacuum forms very, very quickly. And it often forms on the first cycle before most of the air is out of the system. Remember, steam and air are different densities and they will not mix. So if you didn't vent all the air out, in the presence of the vacuum, the air will just expand into the vacuum and actually block the steam from moving. So they got rid of these vents as time went by, and now we have very, very few of these naturally induced vacuum systems still out in the field. The big buildings used vacuum pumps, and this was a great advantage because you take a building again like the Empire State Building, which is running off Con Edison district steam, operating at 2 pounds of pressure, and it's got a vacuum system in there, which means that we have a pump here that inside of itself as an ejector, like we used in the old days with the steam engines, and it will shoot condensate through the ejector and form a vacuum. And the vacuum is formed by sucking the air out of the return lines, through the traps, out of the steam mains, through the radiators, all the way back to the boilers. So this guy is going to suck the air right back to the surface of the water in the boiler. The burner comes on, the system begins to go into vacuum, and suddenly the steam begins to chase this vacuum that's forming. And because we've got this greater differential going from a very low pressure, relatively speaking, say 2 psi, into what might be a negative 3 or 4 psi on the vacuum side, there's your greater pressure differential from one side to the other, so the steam goes faster. High pressure goes to low pressure. So the steam begins to move more quickly throughout the building. So it was a great way in a really big building to get the steam out to the extremities and to get the radiators hot. And also because they were working with the steam pressure to vacuum differential, they also got to downsize every pipe, valve, and fitting on the job. So, for instance, you know, if you needed a 3-inch pipe, well, you get away with a 2.5-inch pipe. Everything went down by at least a half a size, which means that once this thing is a vacuum system, it's always a vacuum system. You can't run it effectively as a pressure system, just trying to push the steam out rather than pulling the air back. Well, you can, but at great expense and with tremendous amount of problems. So this is the challenge we run into. Steam traps don't last a long time. I mean, manufacturers took, you know, maybe 10 years, maybe 5 years, depending on how the building is being used. But when a steam trap on a radiator dies, it just begins to pass steam into the return line. So now you got steam here. If the floating thermostatic trap fails, you got steam here. The steam is heating the condensate, making it super hot. And this vacuum pump is making a vacuum. So in the presence of the vacuum, if the water is too hot coming to it, the pump's going to come on and it's going to cavitate. It's going to flash water into steam inside of its impeller, and it's going to fail. So we got to figure out a way around that. And the way around that is to maintain the traps. Make sure your traps are working. But the problem in reality is that the big buildings, you know, they don't know if they have a good maintenance program, or if it's a cooperative apartment building, you know, some people have heat, some people don't have heat, some people are complaining, other people are not. So they don't do anything. They wait another year. And in that time, you begin to get to a point where the vacuum pump has just failed. And now somebody will go downstairs, and on the vacuum pump, there's a switch that says pump only. Now it turns this vacuum pump into a condensate pump, but it's not making vacuum anymore. So everything in the building is screwed now. I mean, there's no distribution, there's high fuel bills, there's water hammer, there's complaining people, and they'll bring in another contractor. And the other contractor will come in and he'll do something like this. He'll go out and he'll buy a trap, a really, really big trap. It's called a master trap. Anybody that does this is a world-class knucklehead, because what's going to happen now is the vacuum pump is going to pull a vacuum between here and the trap. That's it. And you get this beautiful vacuum here. Now over here, you have now double trapped your return lines. So some of these traps are working, some aren't. When you double trap a return line, nothing moves through it. So the water lays back up here in the system, and it's hammering like crazy. And when it finally does work its way back, if it works its way back, if enough traps fail, this guy then opens up and vomits this super hot water into the vacuum pump and blows it up again. There's so much for Mr. Master Trap and the knucklehead who put it in. So this is never accepted. Don't get sucked into that. This that you see here is a check valve that's just facing this way on a pipe that goes down and fills up with water. Now it's that way because on a system in the springtime or in the fall, when again you got chilly morning and the steam comes on cold pipes, it's possible that just the steam condensing in the pipes on the supply side could induce a deep enough naturally induced vacuum that would be deeper than what the vacuum pump is making on the return side. So in other words, you could have a deeper vacuum on the supply than you have on the return. And when the trap's then open, nothing's going to move. The water will just lay in here. In fact, everything will start going backwards. So this guy, this vacuum breaker, this check valve that's under a water seal, prevents that from happening. Because if a vacuum over here begins to form, this breaks it. So this is the vent line that's going over here, and it connects to the steam header. The two-pipe air vent system that I mentioned earlier, this is what we had at many of the buildings. The Dakota apartment building had this. It was converted to this one. They went away from the pole system. And this is where you'll see one size larger. So it's a supply pipe to a radiator. And this is the return line. In this case, everything's going into wet return. So two-pipe air vent system. Air vents on every radiator. So it's kind of like one pipe steam pitched in the direction of flow toward what are essentially drain lines that go back into the return. So in this case, you'll know it because the supply side is always going to be one size larger than the return side. Here you see it in real life. This is the supply over here. Look at the size of the pipe. One size smaller over here. And the air vent is always on the return side. So it's a one-pipe steam system with a drain. They were used in government buildings and schools and in places that had big radiators, and we didn't want counterflow in the supply main. So two-pipe air vent system. It's the one time when you will see, and they belong, air vents on a two-pipe radiator. Other than that, if there's a steam trap on the radiator, it should never have an air vent on it. This is a two-pipe air vent system in a Manhattan office building. Now, this one was fun because this is the supply line. It's a vertical riser that goes up through the 12 or 13 stories on this building. This is the return line. Notice how this feeds the radiator. Now, they decided to use these thermostatic radiator valves, which was a big mistake. This is feeding the radiator. It goes over to the other side of the radiator and in. This is the return from the radiator. This is going into the main. Now, there is steam in this line, and there is steam in this line. This is normal for a two-pipe air vent system. It's kind of like a ladder where the steam is moving across the rungs. There's nothing to stop it. The rungs are the radiators. So the steam is on the left side of the riser, the radiator, and on the right side. So the steam favors the supply pipes because they're bigger on startup. Once the system is running, there is steam pressure in both of those lines, and it's feeding toward the radiator, and the radiator works because it has an air vent on it. See the air vent right there? That's why the radiator works. Now, they put a thermostatic radiator valve on here to prevent the radiator from overheating. It sensed the room temperature, and it closed. It did its job. So this steam line was closed. But there's steam in this pipe, and there's an air vent on the radiator. So, the radiator just shrugged its shoulders. The steam went into the return, heated the radiator, pushed the air out of the air vent. So the radiator continued to heat. So I got involved in this, and I said to the people, you got to get rid of these. You can't use this type of a thermostatic radiator valve on a 2-pipe air vent system, you have to use the type that goes between the air vent and the radiator, as I showed you earlier. And they said to me, well, who's supposed to pay for that? I said, I don't know. That's not engineering. That's sociology. You know, that's something you're going to have to work out between whoever you hired to do it. But this was definitely a mistake. So again, know what it is that you're looking at before you get involved in it. If you see pipes like this and you don't know what you're looking at, take pictures of it. Go to heatinghelp.com, post the pictures on the wall, and somebody will tell you what it is that you're looking at within minutes. Why should you muddle around in the dark making mistakes when answers are as close as your computer? Believe me, I learned this the hard way. So here's a boiler that's mounted up on a very high platform. The first time I saw this was in an apartment building on Long Island, and I went there with a contractor who was changing the boiler, and he brings me down the basement, and we're looking at this big cast iron boiler that's sitting up on what appeared to be an altar, and it must have been 5 feet in the air, and the boiler's way up there, and the building's at the top of a hill. And the guy says to me, "What? I don't know why they put it up here. Whether they're afraid of floods or something. I mean, it's never gonna. If it floods up here, that we're gonna need Noah." So we had a laugh, and he says, "Can I put the boiler on the floor?" And I said, "Sure. I don't see why not, because I wasn't thinking. I was young and dumb." So he puts the boiler on the floor. What I didn't know was this guy who put this boiler in was brilliant, because he was creating what's called a false water line. Now he's going to create a false water line when we move it, but right now look at the water line of the boiler. It's sitting up on this pedestal about 5 feet up, and this is a 1-pipe steam system. This is an apartment building. This is the lobby. There are doors in the lobby that go into offices and whatnot. And every time we get to an office, the pipe dips into the concrete floor and comes up on the other side. So as we go through, we're going under these doors and back. Now, by mounting the boiler up so that its water line was about a foot higher than the lobby floor, he put all of those pipes permanently underwater. So the steam line was here. This is the A dimension, and everything here is a wet return. Got it? Okay, now my guy says, let's put the boiler on the floor. So he says, okay, put the boiler on the floor. Look where the water line is now. Now it's down here. We just took what was once a wet return and turned it into a steam line with all these pockets that go into the doorways. Well, the first time they run it, the pockets were full of water, and the steam came bellowing through here and took that water and just hammered it, and the hammering was so loud that you could actually hear it outside the building. I've never heard anything like this. And the guy called me up and he says, "What do I do?" So at this point, I do some research, which I should have done in the beginning, and I learned about this phenomenon that the old timers used called a false water line. And a false water line is a trick that we're going to use to make the building think that the boiler is where it used to be. So we do it by taking this pipe here and getting rid of it. We're going to get rid of that pipe, and we're going to create a dam by making this pipe go up and down into the Hartford loop, and then we're going to take some steam and put it into this side, because we've got a U-tube here. You see it? U-tube, this is filled with water all the way across, because now the water line is up here, not there anymore. So this is a U-tube. So there's steam pressure on this side pushing down, and I want some steam pressure on this side, so that the steam pressure over here doesn't blow this water seal. Because without steam pressure over here, it's like a seesaw where you take off one of the kids. This guy's going to go up. So this solves the problem, and that's what we did. It was either that or put the new boiler back up on the 5-foot altar. We didn't want to do that. Now here's an example of this. I want you to follow this old wet return. This was coming in. Now the old boiler water line used to be up high like this. The new boiler water line is down here. So if you follow this arrow across here, you can see how high that is on the gauge glass. So without the false water line, this definitely would have been a steam line. It would have hammered like crazy. So to avoid that, we just bend it up like this. We create a dam. So now the system thinks the water line of the boiler is over here. We spill over here. It sounds really pretty too. It bobbles over the top. It sounds like new age music. And we threw a little air vent in here just to get the air out on the initial startup. That goes down into the Hartford loop. And here's the steam line to equalize the pressure from the end of the steam main, pushing down on the other side. And it worked like a charm. So when you see stuff like this on jobs, just know what it is that you're looking at. So here's a return line coming back, and all of a sudden the pipe just deeks up like this and comes down like that. And you look at that at first, you say, what, are these people crazy? No, they're not crazy. They're building a false water line. There's an air vent right there. So the building thinks that that's it, and all those pipes that are in the lobby level of the apartment building that go under doorways, they're all permanently put underwater by building this false water line.